Hello and welcome back to the course on artificial intelligence. Today we're talking about the living penalty. All right, so here we've got our Bellman equation, and as we've been going through this course, we've been slowly making it more and more complex. So far we've already added these probabilities in here, and also we've added the discounting factor. Now we're going to look in more detail at this side of the equation where we have the reward. Now remember, previously, when we talked about how reinforcement learning works, we said we have an agent and it performs actions in the environment, and in exchange, or as a result of that, it gets a new state in which it's now in and a reward for that action. Well, so far in our example, we've only been getting rewards at the very end, either if we get to the finish line or if the agent ends up in the fire pit, he gets a +1 or a -1 reward. But that is a very simplistic approach to reinforcement learning, and in more realistic scenarios, you will likely have rewards throughout the journey, not just at the very end. You might have rewards throughout the journey. For instance, if it's an AI playing a game, and if, for example, it's like shooting somebody in Doom, it might get points for killing that enemy. Or it might be in a different other game if it overtakes another car or something like that, just because of the rules of the game, not because of its way of analyzing the game, but actually the game is structured in a way that it's reinforcing, it's giving points for doing certain actions even before the game is over. So scenarios like that are very common, not just in games and also in real life. And that's why we're going to introduce something similar into our example, a simplified version of that, but nevertheless a reward that is continuously given to the agent throughout the game, not just at the end. And the way we're going to do it is by looking at the other tiles. So right now we only have reward +1 at the final tile and reward -1 at the other final tile, the fire pit. But now we're going to add rewards in every single tile. We'll add a very small reward. It'll be -0.04, and as you can see, it's negative. So every time the agent moves, he'll get a negative reward. And that's why it's called a living penalty, because no matter where he goes, he will always get this negative reward, except for these final tiles, because that's the end of the game. And so here you can see the reward even on this tile is -0.04, but that doesn't mean that he starts with that reward. He only gets this reward, and this is important to remember, he only gets this reward when he enters a tile. So whenever he performs an action, he goes here, then he will get this reward -0.04. And then if he comes back to this tile, he'll get another -0.04 reward. And so the longer he walks around, the more he accumulates this negative reward. And therefore, it is an incentive for him to finish the game earlier, as quickly as possible. And so now let's have a look at how our policy, or how the agent's policy, is going to change depending on what value we set for this reward. So here are 4 environments, and in each one we're going to explore a different reward. Now we're not going to do the calculations, we're just going to project the results, and you will see that intuitively they make total sense. So here we've got a reward for any step, or for getting into any state, is equal to 0, just as what we've seen before. Here the reward is going to be -0.04, what we just introduced now. Here the reward will be -0.5, or the living penalty will be -0.5, so much higher, you can see, than here, more than 10 times greater. And here the living penalty will be -2, so even more than the reward you get for jumping, or even less than the reward that the agent gets for ending up in the fire pit. So let's have a look at how the actions, or the optimal policy for passing this environment will change depending on this reward. So this is our original policy. And as you can remember, we had these 2 very interesting and even a little bit weird decisions by the agent, but which totally makes sense if he can live for as long as he likes, if he can just travel around for as long as he wants without being penalized for staying alive very long. Why not? Why wouldn't he just go into the corner here, into the wall, and just keep doing that until it so happens that he goes this way, and then he will walk around. And same thing here. It's much safer for him to jump into the wall, hoping that one of these will come up eventually, and then he'll go to the finish line anyway. Because by choosing these 2 actions, he doesn't risk getting into the fire pit. Now let's see what happens if we add a reward a negative reward for just being alive, for making a step, for making a move. So here you can see that instantly these two changed. Now the agent doesn't want to jump into the wall. He is more likely to risk getting to the fire pit, having a 10% chance of jumping in here, but he will go forward. Because every time he jumps into the wall here, if he was going to be doing it here as well, every time he jumps into a wall, he performs an action, he ends up in this state with an 80% chance, and that means with an 80% chance he will get a minus 0.04 reward, meaning that a lot of the time he's going to be getting this, accumulating this negative reward. Same thing here. If he jumps into the wall, waiting for that moment when he will actually be randomly moved to the right, if he keeps doing that, he will accumulate this negative reward, and that the result of that, if you perform the calculations, you'll see that the result of that, the expected value like of that approach, jumping to the wall, is worse than taking the risk of going forward and actually ending up in the fire pit. So he changes his decisions in these two blocks to instead move forward and here move to the left, even though there's a risk of jumping in the fire pit, simply because now the longer he's alive, the longer he will accumulate this living penalty. In the next environment, now we're increasing the living penalty to even a greater number, minus 0.5, and let's see what changes here. So now you can see that compared to this environment, the only thing that changed here is that this arrow is pointing to the right. And what that means is that now it's no longer a good option for the agent. Oh, actually also this arrow was pointing to the left, and now it's pointing to the upwards. So now it's no longer a good idea for the agent to go around from here, go around all the way, because if he goes around all the way, yes, he's safer. There's no chance of getting into the fire pit. But at the same time, or there's a less chance of getting to the fire pit, but at the same time, he will accumulate quite a substantial negative reward as he walks around. So the path is too long. So that forces him, even whether he's here or here, to take the shorter route to get here, even though he has a much higher risk of getting into the fire pit, because as soon as he ends up in the square, there's a 10% chance of getting to the fire pit. According to his calculations, it's just the expected value of this approach is better than the expected value of going around, simply because we've increased this living penalty. And finally, we're getting to the example with the living penalty of minus 2.0. So here, I would encourage you to pause the video now that you've seen how the policy has changed as we increase the living penalty. I encourage you to pause the video and to think for yourself, what will happen in this scenario? What do you think the optimal policy will be, given that the living penalty is so high? So I'll let you pause the video if you'd like to. And now I'm going to jump into showing you the solution. So in this case, if you increase the penalty to minus 2.0, it's so high. Remember that the penalty here is only minus 1.0. It's so high that the agent just wants to get out of the game in any way possible. Even if it's just by jumping into the fire pit, he will do it. He will be like, every time I make a step, every time I end up in a new state, or every time I make an action, I end up getting a minus 2 reward. So what's the point of trying to get to the finish line if from here it'll take me 2 extra steps? I'm just going to go here and then straight into the fire pit, because that way my reward is going to be less. The negative reward is not going to be as bad as in the case of just making additional steps. So you can see that adding this living reward, and depending on the value of the living reward that we're adding, the results are going to be different, and the agent is going to select different policies. And that's basically how the reward value is incorporated by the Bellman equation, even when it's not just at the finish line or at the end of the game, but even throughout the game. And once again, it doesn't have to be on every single in every single state. Depending on the environment itself, it might be given to the agent at certain specific states, not at every state. But in our simplistic example, we're just using rewards at every given state to illustrate this concept. So I hope you enjoyed today's tutorial. And as you can see, we've already made our Bellman equation quite sophisticated, and now it can be applied to many different scenarios. And I can't wait to see you in the next tutorial. And until then, enjoy AI.